Hi, everyone. Thank you so much for joining. We have something very exciting to share you. But before I start, I just wanted to acknowledge the multiple NVIDIA internal teams and also external partners that we work together to make this amazing product into reality. So thank you. So I'd like to talk about what we are going to share today. So I'm going to kick it off and talk about motivation as to why we decided to create a new product in inference serving. But also at the same time, I would like to talk to you about the key features and benefits. And then next, Neelay, who is our principal architect, is going to talk about the architecture. And he's also going to give us a preview of the workflow of Dynamo. Then Tame is going to actually show you how you can actually use Dynamo in action. And then lastly, Ryan Olson, who is a principal solution architect, is going to go a deeper dive into the API of Dynamo. And then I'll come back and try to introduce some next steps. OK, so I wanted to kick it off with a motivation. As Jensen talked about today in his keynote, we've already entered the GenAI era, but now we are entering the reasoning or test-time compute or inference compute era. And because of that, you actually need a lot more compute and memory. Because inference compute or reasoning requires the model to actually think during the inference time. And so the compute or the memory requirement is only growing. But at the same time, it's quite difficult to actually scale these type of models. And so DeepSeek shared their implementation of DeepSeek v3, which is their base for the reasoning model R1. And the way that they deployed this particular model in their data center is that they did something called disaggregated serving, where you separate prefill and decode phases of LLMs. And then they decided to assign about 32 GPUs to fulfill the prefill computation. But for decode, they actually employed about 320 H800s to do this. And so we think that this is actually super hard to, the idea behind it is actually simple, but the implementation is actually quite difficult. And there hasn't really been a good, reliable, production-ready solution out there that's open source. So that's what we think is a problem. And then when you think about it, before GenAI or reasoning, having a simple router that does round-robin routing was perfectly fine, and it was actually quite performant. But we're actually leaving a lot of performance on the table if we do this, because there are so many other things that are specific to LLMs that we can leverage. And lastly, with LLMs, they have a heterogeneous inputs. And so you could happen to have a situation where at certain point, you're only getting specific length of input. So say if you look at sequence 1 and sequence 2 here. But maybe later, you're actually getting hit with a super long context length. And if you imagine this happening at a data center scale, it's really hard to stop your deployment and then manually reconfigure it and then deploy again. And so these are some of the problems that we want to address with our new product. So we decided to tackle these problems. And we, as you heard from Jensen's keynote, we have a new product called Dynamo. And Dynamo's mission is to accelerate distributed inference in the data center. And we think that there are 3 key areas that we have to focus on. The first one is job scheduling. Second is how you manage the memory within the data center. And then the third is how you transfer data in that large scale. And so very soon, I will talk about some of the key features that we have implemented for, say, for example, for scheduling. We implemented smart routing that's aware of the KV cache in the data center. We also implemented KV cache manager for being able to manage the memory much better. And it will utilize all the multiple hierarchies of the memory that is present in the data center. And then lastly, we actually have a new data transfer library that we created that lets you transfer data with a very low latency. So We think that we have key features for all these three foundational areas, but we just wanted to highlight that I kind of talked about disaggregated serving the previous slide, but disaggregated serving really requires you to have a very strong foundation in these three areas: scheduling, memory management, and data transfer. And so we believe that the features that we have currently launched with Dynamo, you can actually take advantage of disaggregating feature and be able to deploy your LLMs with this advanced technique. So next, I will talk about what disaggregated serving actually is. So here, the idea is actually quite simple, but the result or the performance that you can gain from it is actually quite phenomenal. As you probably know, LLMs have two phases. The first phase is prefill, and so it's a phase until you do all the computation of your KB cache, and then you start producing the first token. And then once you start producing the first token, then you go into decode phase, where you can actually decode the incremental tokens that comes after it. But if you look at the compute characteristics of both, prefill is a compute-bound process, and then decode is actually memory bandwidth bound. And so they're quite different. And the idea is that can we actually separate the two phases? And if you do so, then you have a unique opportunity because you can actually take the independent or now the disaggregated phases and apply different types of parallelism that is more suitable for prefill and decode. One caveat here is that you still need to now figure out how to transfer the KB cache between prefill and decode now that they're separated. And that's the reason why I talked about how in that diagram, you need to have that strong foundation where you can do all job scheduling, memory management, and then also data transfer. And so I'll show you later how the KB cache transfer is facilitated by the new Inference data transfer library that we created. But disaggregated serving, it has two interesting characteristics. And so it will perform really well if you have a large model or if you have a lot more GPUs to use. And the reason is that because you now separated the prefill and decode, you have a lot more opportunities to apply different configurations for parallelism. And so with all the combinations that you can consider, you can actually figure out the more performant configuration that can scale better for you. And then the second part is that when you look at the in-flight batching versus disaggregated serving, if you have a little bit more, or if you have a decode-heavy task, then the way that in-flight batching and then also disaggregated serving allocate the resources is the same. And so it turns out that it usually works better if you have a much longer context to process. So now, one more additional benefit is that now that you've disaggregated, you actually have a choice, and you can make a trade-off. So prefill is measured by the time to first token, and decode is measured by inter-token latency. And so say that you have a SLA requirement that you want to optimize, you can actually optimize them separately. So if you want faster time to first token, then you can increase the prefill workers. And you can do the same thing for inter-token latency if you want to decode faster. And then you can make the trade-off between the ratio of prefill and decode if you want to increase the output token throughput. And interesting benefit that you can also have is you can also pair up different types of GPUs for prefill and decode. And so we met some Chinese customers this year and last year that they were pairing up H800 for prefill and then H20 for decode. And that actually brings a lot of cost savings. So you have to think about the performance envelope of, say, prefill GPU should have it's OK to have a less memory, but you want to have more compute. And then for the decode, you want to have more memory bandwidth. So next, I wanted to show you the benefits of disaggregated serving. So here, we did a test. We ran R1 distilled 70B using 3,000 input sequence length, and then about 150 output sequence length. And the plot that you're seeing is basically a trade-off between throughput and latency. So on the y-axis, you see tokens per second per GPU. That's basically throughput per GPU. And then the x-axis, tokens per second per user, that's latency. So what you're seeing here is a graph of a trade-off. And we've already calculated all the different configurations that we tried. And we are only taking the proto frontier of the configurations. So if you see the first plot, which is comparing the one node disaggregation against aggregated setup, you can see that we gain about 30% throughput per GPU. And this is the reason why, and you've probably already seen 2x number on the other side. The reason why you actually get smaller gain in a single node is because it just doesn't have a lot of room to do multiple configurations of parallelism. And so as soon as you move to the 2 nodes, you're seeing that there's a big jump in terms of performance for throughput per GPU. And we've seen in our actual runs going up to 3 nodes and 4 nodes and so forth, you will actually get incremental benefit above the 2x line. And so what this is actually showing you is that because we measured it per the throughput per GPU, you're actually scaling better than linear scale, which is incredible. And so this is why we think that this is a key feature of Dynamo. And there are some more advanced features that we'll show off. Tommy is going to give a demo for you. Things like conditional disaggregation and auto discovery. And so I'll let Tommy talk about the exciting stuff later. OK, so next up is about scheduling. And in this case, we are going to talk about routing. And here at the top, I'm giving a simple example here where we're doing like a more traditional balancing or load-based router. And so say, for example, if you have a query that says, what is GTC? And say that the worker 3 actually has a relevant KV cache that corresponds to what is GTC. It's a bit of waste because in this setup, because the load for worker 1 has the lightest load, the query will get routed to worker 1. But in fact, you can actually leverage the KV cache that's in worker 3 to expedite the processing. And so if you look at the bottom, now the difference is that we try to calculate the KV cache match rate for each worker. And the way that we do it is we map the KV cache with a registry using a radix tree. And so we'll be able to figure out the KV cache hit rate. And then the router is going to be aware of where to route the work to the corresponding worker. And so if you look to the right, we have exciting results. We actually didn't try to use simulated or synthesized data. This is an actual real data. It's about 100,000 requests that went to an R1 model. And then we wanted to test out our KV cache aware routing mechanism. And as you can see, it dramatically speeds up the latency relevant or related metrics. So things like time to token, it turned out that it's 3 times faster in average. But also, average request latency got cut down by 2x. So this also, we think that this is a key feature of Dynamo. Next, I will talk about memory management, and something that is very closely tied to memory management is data transfer, so that's coming next. Here, in a data center scale, you can consider maybe 4 different major types of memory hierarchy. And so if you look at the top, you have HBM, and then you have the system memory, the local SSDs and object storage. And we all know that if you can smartly utilize this multiple hierarchy, because if you look at the HBM, it's going to have the smallest storage amongst the rest of it, but it has the fastest data transfer bandwidth. But if you go to the bottom, network storage is going to have the most storage, but it's going to have a limited bandwidth. And so if you put in some intelligence as to how you can actually move the KV cache around these different types of the memory hierarchy, then you can actually dramatically speed up the time to first token. Because instead of recomputing the KV cache, you can actually load and prefetch the KV cache and then get that processed and then start decoding right away. And so this is phenomenally useful if you're doing something like multi-turn chat or if you have a long context, because you have a lot more space to store your context. And then also, if you are aware of how the KV cache should be processed at which time, things like structured workloads or agentic workloads, then you can actually figure out when to offload the KV cache and then also prefetch before you need to get it processed. And so the result that we are sharing here is an early implementation that we have on with a Dynamo. And so we kind of submitted about 80 users with 1,000 input sequence length and then 100 output sequence length. And then we basically did a multi-turn of 10. So here you can see at bulk with this many users, even with the prefix caching turned on, you are going to get speed up of 1.6. And so this is another innovation that we have. We are actually going to make it, so right now we have it available for offloading to system memory, but we are going to release something that does offloading to local SSD and then network storage all together. So that I will try to discuss that in our next steps. So something that is very closely tied together is data transfer. And so in a disaggregation case that I talked about before, you need to be able to transfer the data between multiple nodes so that you can pass the KV cache from prefill to the decode node and then be able to process that really fast. And so the new library is called NIXL, NVIDIA Inference Transfer Library. And it speeds up the transfer between the multiple nodes by requiring less synchronization and also being able to batch the KVs. And it also has a support for more inference-appropriate workloads. And so it can support dynamicity. So if you scale, you need to be able to add and remove the workers very quickly. And then, like I said before, you need to be able to transfer data not just between the GPUs, but between the multiple hierarchy of the memories here. And so you can actually offload everything or KV cache through the hierarchy that you're seeing here, all the way to the network storage. And then this serves as a common layer. So it supports RDMA, so InfiniBand and Ethernet, and also TCP. And then we have plans to support AWS EFA. And just wanted to show, this is basically plots showing the difference between NIXL on and NIXL off applied to this aggregation case. And so you can see even just implementing this library is going to give you an amazing performance benefit for first time to first token, but not only that, even output token throughput benefits. So to sum it up, here is what we currently have in Dynamo today. First, the GitHub link is actually ai-dynamo/dynamo, but we decided to give you a short link so that you don't have to type all that. So if you go to nvidia.com/dynamo, it will direct you directly to that GitHub repo. Under the AI Dynamo organization, you should see the Dynamo stack, but also you should see NIXL, the inference data transfer library. And the reason is that we took your feedback and we really wanted to make a modular product so that you can actually implement these things. Not everybody's going to need everything that we provide. And so we're trying to make sure that you can actually take parts of our stack and then be able to run it with your inference stack. Something that we're doing completely different now is that we decided to have Apache 2 license. So before, if you look at, say, a project like Triton Inference Server, it required you to sign CCLA, and that was a very complicated process. You don't have to do that anymore. And we also have a public CI in place. So if you contribute, and then if you want to check whether your code is running, now you can do that. And we also decided to go completely just prioritize prefill on PyPI. And so we think that you should be able to get this running by doing pip install. And so we are going to really prioritize prefills over containers. And this stack is also special because we took a lot of feedback from our customers. I think that there is a transition happening in the industry to Rust. And so Rust gives you a benefit of memory safety and concurrency. And so we decided to write a lot of the stack with Rust. But for developers, we also want extensibility. And so we then decided to provide Python bindings, and you should be able to get both of the best of both lands using that implementation. And lastly, we actually have a Discord set up, so you can directly talk to our developers and then also solution architects. And so if you go to this link, there is a badge that you can see, and then you can just click on that badge and then be able to get onto our Discord server and then start talking with our experts. We then also really focused on our user experience. And so this is a CLI that we are providing. There are 4 subcommands. With Dynamo Run, you can just quickly get your server set up and run. And then you can provide the input and output and model. It's that simple. And then the second CLI is a Dynamo Serve. And so with this CLI command or subcommand, you'll be able to construct a graph of workers and then serve. And we know that a lot of developers want to deploy this into production environments, such as Kubernetes. And so we have 2 subcommands that follows. It's an early implementation, but Dynamo Build is going to containerize either the whole graph or the parts of the graph into multiple containers. And Dynamo Deploy is going to deploy it into Kubernetes. But we are also letting developers specify their resources in Python decorators, so to make it a little bit easier than just using YAML. So as features, we currently support 3 backends. So Tensor, DLMM, VLMM, SGLang, they're all supported with a varying degree of support. And disaggregated serving and KB cache routing is supported for Tensor, DLMM, VLMM. And we are in early stages with the KB Manager with the VLMM implementation. But a new, better implementation is being worked on at this point. And then finally, Nixel is supported for RDMA and TCP. So we are very excited about this product. Hope you get to try it. And then if you like it, please give us a star on GitHub. I'd like to then pass the mic to our principal architect, who is going to talk about the architecture and then the workflow. Thank you.
Hello. Testing. Thank you, Harry. So, I'm Neelay. Good afternoon, everyone. So go to the next slide. So we talk about the architecture. I think whenever we start something new, I like to kind of think back about where we've come from, right? And kind of why are we making the changes we're making. So last year, almost a year ago, GTC 2024, I was on a stage similar to this, talking about large language models and what they had brought to change in the landscape of inference serving. At that point, it really occurred to me that there's 3 kind of big things that were happening. One, models were just getting huge, right? So techniques for optimizations that you had for single node, single GPU models weren't scaling well. The second is, the types of batching and the types of model optimizations you had were changing. You had things like continuous batching, you had page detention. And finally, the developer community was moving so fast, right? Every week, new models are coming out, new techniques. We had a mixture of experts, we had Mamba, we had different snake-related things every week. And so the pace was fast. So what has changed in here, right? I think the biggest thing that's changed is that we started to see that the optimizations you need to apply, and I think Harry alluded to this, is really at the system level, right? So no longer is it fair to just optimize your model or optimize serving for a single node. You've got to really think about the entire system, right? New ways of routing, new ways of distributed caching, model disaggregation, resource planning, right? At the data center level. Not just a single node, not just a single server, but at a system level. Okay. Interestingly enough, I think the other 2 things have stayed the same, right? So the pressure of model size is still going to be there. Also, the pressure of developer velocity is going to be there. So as we evolve the system, we can't leave those 2 things behind. Again, a year ago, I was talking about the move from local development to deployment, right? So when you're developing something locally, your key challenge is probably just to make sure it works, right? Make sure your model has the accuracy you want, your pipelines, pre and post processing is working correctly. When you go into deployment, and this is thinking about a single inference server, you start to look at how do you optimize your model for certain backends. So you may start in Python, but then you may go to TensorRT, for example, right? And then again, the key challenges are around batching and resource optimization. So where we are a year later. As I mentioned, the challenges are becoming more system related. And so we need to move from developing on a single system and a single inference server, where your key challenges are really single node performance. And if you spend any time with Triton Inference Server, that's really been very much the focus of Triton Inference Server, is how to get the most out of a single node, multiple GPU, sure, but didn't really scale to multiple GPUs. So now when we go forward, right, we're moving into a Dynamo, which is the distributed inferencing serving platform or framework, as you like it. And now we got to start thinking about modularity, right, in data center deployment. And I'll talk a little bit more about that. So what do we need from a distributed inference serving framework? Okay. Well, we need to be modular, right? As Harry mentioned, we don't want a one-size-fits-all type of solution. You should be able to take pieces of it and reuse them or remix them to meet your solution needs. Second, we want it to be flexible, right? We want it to be easy to customize. So definitely, we're Python first, right? You can take parts of the system, change it up in Python, and customize it for your system. Scalable. Individual components need to scale independently. So as you can see, this picture is a much more complicated picture. There's a lot more boxes on it, a lot more processes, right? The idea being that we break up, for example, the front end from the back ends, so you can scale them independently. Finally, things need to be highly efficient, as always, right? We want to have highly optimized worker-to-worker communication, which is really device-to-device. And we want to be Rust native in this case, so highly optimized core in Rust. And I try to make that little bit of distinction, right? So we're Python first, because that's where the developers are, but that doesn't necessarily mean we're Python native, right? So where we need to, we're going to push into a system language, and obviously Rust is the best system language today, right, in terms of memory safety, et cetera. So the architecture. So I think of it broadly into two pieces, right? There's the components, and there's a set of infrastructure underneath. You know, we've called them communication planes in the past. You can think of them as infrastructure services, but again, they support the components, okay? And I'm gonna just walk through a simple example of how that works. So in this case, we just got a simple API server, a router, a worker. And again, in each of these, you'll see a highly optimized Rust core. And then on top of that, either a Rust code, because you can code in Rust, or a Python piece of code, right? So discovery. So at the beginning of when the system starts up, each of the individual workers or components register and watch each other through the discovery plane. And today we're using etcd for this. Okay. So an example, like the API server is going to register and watch for routers to become available. Because it's a totally dynamic system, right? So if it starts up and there's nothing there, it will wait. And if you send a request to it, it'll give you an error saying there are no routers available, right? Eventually a router will show up, it registers. It's also going to start watching for workers. Finally, the workers will spin up. I guess, obviously it's not in that order. They can come up in any order you want. But then the worker will initialize the actual LLM, async engine, and then the system becomes fully functional, right? Again, if any of these components goes down, you can replace it, right? It's fault tolerant in that sense. Next, we got the request plane. So we kind of translate from, let's say, an external API, like OpenAI, into internal Dynamo requests. And that's how we can have highly efficient communication within the system, but still have a domain-specific API to the external world. Okay, so again, API server is going to take the request in OpenAI format, translate it into the internal format. Router is going to take those requests and, as Harry mentioned, kind of use an algorithm that combines both KB cache aware routing as well as load matching to get you the best available worker. Okay, and finally, the worker is going to do the work. Right, that's why it's named a worker. So it'll execute the request. And we still have all the optimizations you have for a single node here, continuous batching, prefill, decode, disaggregation, et cetera. So those aren't left behind because this worker is just going to be containing the engines that are already optimized. Next, you have events. Right, so an API server, I kind of combine things. We might have a separate metric server, but just imagine that this is also going to have a Prometheus endpoint. It will listen and aggregate events and metrics. Okay. The router is the key piece here, is it's actually going to be listening for updates from the workers and to understand the global state of the KV cache, right? That's how it's going to know how to route. And finally, the worker itself is going to be the event source. When any KB cache blocks gets entered or exited, or stored or evicted is the right words, the worker is going to send that into the events bus. And again, we show specific listeners here, but really anybody can listen to anybody else. Finally, the data plane. And again, this is one of the key interesting new technologies, right? We're leveraging the new transfer library to really ensure that where we need it, so an example for like larger requests, we can get device to device as close to zero copy transfers as possible, right? So for an API server, for small requests like LLM serving requests, you may not need it. You may just push that straight into the request plane. But for larger, like let's say images or streaming, we may end up using the Nixle transfer library. Okay? The router, in this case, is not really directly participating in data, right? It's not going to go from the API server through the router to the worker necessarily. The worker can talk directly to the API server, right? And that's what we mean by the point-to-point optimized communication. And finally, in most of the examples you'll see today, the key thing that we use it for today is around device-to-device communication of KV cache, right? We know that's a big size thing. We know we need to do that efficiently, so we have the new library to support that. Okay, a little bit more about Nixle. There's kind of three really key interesting things from my perspective. It's really cool technology. The three things that I like to think about when it is, one, it handles memory for you. So you register memory of your application with the communication library, so that makes it so you don't have to do zero copy, or you don't have to make copies, right? You put the data straight in the buffer. That's the same buffer that the communication library will use to send it out. The second piece is that this metadata handler. So we already described a little bit that this is a peer-to-peer system that doesn't require a central controller. So unlike MPI or Nickel or some things like that, which require kind of a static world size, this metadata handler can be expanded during run. So basically the way we do it is these agents come up in individual processes. They transfer the metadata. That allows them to keep open connections, so they don't have to reconnect to the peers. And again, allows it to discover peers as they show up. The third thing is that it's also a modular library. So numerous backends, UCX being one of them, but we were going to expand it. But it's also possible for external developers to expand it, right? So if you have your own transfer mechanism that you want to do, you can just plug it into the backend, and then the rest of the system stays the same. 2024, I was really excited about this slide. So we got to 6 steps to run an LM. But as Harry mentioned, it starts with the Docker, and it takes a little bit of time, and really 6 steps just to get an LM going. And it wasn't even OpenAI at this point, right? So where are we today? So with Dynamo, we're getting it down to 5 steps still, but 5 steps to go from your local machine to Kubernetes. Right, so it's a lot, same number of steps, well, less steps, but a lot more functionality. We're really excited about this, so I'd go ahead and put this on the slide, is the pip install, right? We're developers just like anybody else, so we really love that ability, right? Just go straight into pip, don't have to build a container, don't have to mess around with that. I still like containers, but anyway. Next, Dynamo run, right? You want to get quick feedback, right? You want to see if your model works in Dynamo just to start, right? So now we've got a new CLI subcommand called Dynamo run. It's pretty cool, right? You can just give it the model name. You don't have to pre-download your model. You don't have to convert it. There's no engine building here. And you get a working prompt, right? In this case, I asked it to do a poem about a crab and a snake coming together and becoming best friends. Probably a little bit on the nose, but in any case. And it doesn't stop there, right? So now you've got something running, you want to serve it. So in this next example, we're going to show kind of spinning up a local set of processes. In the previous one, you don't actually have the full set, but this case, you're going to have a router, HTTP server, and 4 workers. So the cool thing here, I don't know if I go back, but you can just say basically Dynamo serve and tell it I want 4 workers and give it the same model name, and it spins up everything for you. Right? And yep, now you can see all the 4 workers coming up. And you can see this dynamic part too, right? So one of the routers is looking for, it says like there's currently 0 workers, but there's required 1. It's waiting for workers to be ready. Now you see the VLM worker is kind of getting installed and initialized. And there, oh, and then I turned it off. Wait. So in between here, because I didn't show the actual curl requests, you'll see actual requests getting added. So added request, average prompt through, all the metrics and stuff happening. And Tommy will give you a little bit more detail of these things as well. After you've served, then maybe you do want containers, right? So Dynamo now has a feature to be able to build kind of specific containers for your deployment graph. In this case, you can containerize your hello world or your large language model, and then get it ready for deployment. Finally, the last piece of this is a one line to deploy to Kubernetes. This is something we're actively just kind of still developing, because it's an active project, but coming soon. So this is the kind of leads out to the final piece, right? And with that, I will turn it over to Tommy.
Thanks, Neelay. Hi, everyone. Thank you all for being here. Neelay introduced Dynamo CLI to us, specifically Dynamo Serve. So we are going to use Dynamo Serve to show about the performance optimization techniques that Harry talked about, how we can use those and integrate it in Dynamo. So a couple of them, like that Harry mentioned, are listed here, and we will go through each of them one by one. The first is disaggregated serving, KV cache-aware routing, and then KV cache block manager. So for disaggregated serving, it's all about like separating the prefill stage of the LLM inference to the decode. So in Dynamo framework, what we have to support disaggregated serving is that we will launch 2 separate worker processes, VLLM worker and the prefill worker. And we will see how easy it is to set up this kind of an environment in a couple of next slides. But let me go over the logic quite a bit, like how they interact. So when the VLLM worker sees that there is a request, it, based upon the certain criteria, it decides whether it should run the prefill of this request locally, or should it like port it to the remote worker, which will run prefill for it. And while the prefill worker is calculating the context of the request, it's free to like execute other requests. So once like the prefill worker has the context ready for the request, it notifies the VLLM worker and uses Nixel to like provide the generated context back to the VLLM worker. Upon receiving this context, the VLLM worker can schedule this decoding and return the final response. So this is the conditional disaggregation which Harry was talking about, because like the disaggregation only like there are certain criteria where it gives us improvements when you have like a large context, a large input token length. So we will see now that how to deploy this in Dynamo, sorry. And yeah. So we will go through certain commands and show that how we can launch this deployment and send some requests and see what happens at the server. So the single line command to launch disaggregated deployment is this. We just point it to a disag graph and provide it certain configurations to launch this disag graph. Now let's go do a deep dive into the graph, like what we provided the Dynamo serve command. We see a front end which links to a processor, which links to a VLM worker, and which links to a prefill worker. So how Dynamo sees this is as this. So HTTP here is the API server, which Neelay was mentioning. And then we have another process for pre and post processing, which tokenizes and detokenizes the requests. And right now, for disaggregated serving, it will talk to the VLLM worker. VLLM worker would decide whether it needs to run a remote prefill, and the same thing summarized here. The configuration, like what is the configuration that we provided? So the front-end configuration looks like this is the model name. This is the endpoint that I need to hit. And this is the port where the API server would listen to the requests. For processor, currently we are using round-robin router. We will go to KV cache aware routing later, but for this part, we will use round-robin. And the VLLM worker configs look like this. We have to enable conditional disag. We have to enable remote prefill. And the condition that we are currently going to use is like max local prefill length is 10. So if the request smaller than token size 10 comes, then I should still do the local prefill instead of remote prefill. And you can see the KV transfer config there, Dynamo Nixel connector, which is using our new Nixel library. And the prefill config is the same. We tell it like you will be getting the data from Nixel, and that's it. So once you launch this command, Dynamo serve these graphs, you will see a bunch of logs coming, and it shows that okay, the endpoint that you requested has been added, and the HTTP server is up. And over here, you see that the VLLM worker, the prefill worker, they have loaded the model, and they are also initialized and ready to serve requests. Now we will send a short prompt, and this should ideally not trigger the disaggregated serving. So we just see that normal, the prompt, the request got added to the engine, and all the prompts were generated by the same engine. The next, we send a big, this is the response that we get when we send that hello prompt. So next, as a next experiment, we send a very long token length prompt. It's, to be precise, almost 193 tokens. And this should ideally now trigger remote prefill. We see the logs, again, on the server side. It says that, oh, it found the input had 193 tokens, so we should be running prefill remotely. And that request gets added to the remote worker, and then whenever the results are ready, this VLLM worker pulls the request from the queue and loads it into its engine and run the remaining decode steps. So this is the final message that we get. So yeah. And another thing that was talked about was how configurable these or scalable these technologies are. So the previous one just launched specific number of workers, but usually in disaggregated serving, we might need more prefill workers. So once you have the deployment working, you can just launch a new prefill worker, and it will start listening for the new request to the same prefill queue and sharing the load so that it doesn't get, the TTFTs don't get boggled down. So this is how we kill the deployment, all the parent processes of this deployment would be cleaned up right now. With that, disaggregated serving tutorial is done. We will move next to the KV cache aware routing. So Harry did talk about KV cache aware routing quite a bit. But yeah, one thing I would like to talk more about is the KV cache router needs a global view of the entire workload. So once it sees the query, simply saying that, okay, there's the highest KV match with the worker 3, then I should send the request to worker 3. that should not be the correct way of handling things. We have a mechanism in Dynamo where we calculate the score of each worker, which we calculate as like, okay, this is the query, the tokens come, and now with that prefix cache tree, we know how much cache hit we will be getting at each worker, but we also need to know how much load they are currently under. So in this case, even the worker 3 had the highest KV match, but because it was under the highest load 80, its score was lower than the worker 2. So we will route the request to the worker 2. Now, these are certain steps to use KV routing with Dynamo. Same thing, same single line command. You just point it to another graph and another set of configs. When this command is launched, you see a new prompt, new log message coming, which is called KV router initialized. Over here in the graph part, there is another component, KV router, which a processor links to before VLLM worker. So how does Dynamo sees it? It sees it like this. There is an HTTP front end, then pre and post processor, and a set of VLLM workers, which we need for this demonstration purposes. And each of these VLLM worker and another KV router, we will go to the next things later. But the entire the logic of KV router is VLLM workers are configured to publish KV events and certain metrics, which the KV router keeps track of. And upon receiving a request from the API server, pre and post processor queries, which would be with the given incoming tokens, which would be the best worker to run this request on. And the KV router returns that worker's ID, and the pre and post processor route the request to the specific worker. How is it enabled in the config? You need another service called router. And in this case, I have set it as min workers to 2. So the router would not start sending the request to any of the workers till it sees that there are 2 workers up. For the worker side, so that they can emit all the KV cache events and the metrics and everything, we need that router KV specification. And because we are routing the request with the highest KV match, we need to enable prefix caching to make it to see the performance improvement and see the caching work. For this demonstration purposes, I will be using the 2 workers, which has been specified in the service args. So I have this deployment up, and I would like to demonstrate that the KV cache aware routing is working. So what I do, I created 2 clients. One client would send the same prompt again and again, one after the other. Client 2 generates random prompt, one after the other. The load isn't high because we have 2 workers, we have 2 clients who are just sending 1 request at a time. So the router sees that the KV match is the highest with a specific VLLM worker, and we see, which in this case is VLLM worker 1, and the metrics that get reported for the prefix cache hit rate is 96.55 in this case. So the identical requests are all going to VLLM worker 1. The random requests for VLLM worker 2 are just giving no cache hit rate because it's all random that's being sent. Now for the demonstration purposes again, we kill this deployment, start the same deployment but without the router. And by default, it uses round robin. So now what happens when in the same setup, the 2 clients, both the workers are seeing some prefix cache hit rate because the identical requests are hitting both the workers. So we also have a metrics dashboard where you can see all these metrics in nice Grafana visualizations, and you can determine what should be your configurations for the best prefix cache hit rate depending upon your workload in real time. So yeah. The next piece that I would like to cover is the KV Cache Block Manager, which Harry mentioned that is in nascent stages, and we are working on getting a better distributed version which can work across the node. So for the numbers that Harry showed, what was done was that we had created some KV cache pool on the host and SSD memory, CPU memory and the SSD memory. The device memory was left free. So all the KV cache blocks were pushed downwards to the lower memory levels, keeping the device memory free so that they can handle more requests and give better throughput. All these executions are like asynchronous. So async put, async get, everything is asynchronous, so it doesn't impact the real-time performance. Whenever the inference engine needs the same KV cache block, it can be pulled from SSD or host memory, wherever it is the closest. It's like the entire caching, CPU caching. Earlier, Jensen mentioned Dynamo to be the operating system of AI, and I think this is something that matches. It's still like in a very nascent stage, and we are working on making it more distributed and more robust. But this was the scenario that we used to get those numbers. Next, I will hand it over to Ryan to go over the API deep dive.
I am the crabby one. Ooh, so definitely the crabby one. So I am both a solution architect and an engineer. And before I go into the code, because Jensen says, at GTC you pay and you get hit with equations and you get hit with code. So these guys have done a great job of giving you the why, and then the kind of the how and like the overview, which was actually those slides were amazing. And then Tanmay showed us that we built all this LLM stuff on this thing. This thing is Dynamo, and it's our data center scale inference strategy, but it's also the library underneath. And these slides are going to just give you a little bit of insight on how we actually built those tools. So the scalable components that you're going to have to play with, to go and build your own tools. But before I jump into that, I'm going to put my sales and solution architect hat on that says if you're a NIM customer today, you're probably wondering, what should I do about Dynamo? Dynamo is coming to you soon. If you are thinking about, you've presented all this amazing stuff with KV-aware routing, and you've presented disag, what should I do with it? Like, I don't know. If you are doing multi-turn and agentic workloads, you definitely want to look at the KV-aware router. Like, you're going to get instant value from that. So if those are your workloads and you're not in NIM and you're in Triton today, definitely consider thinking about migrating or looking at it and playing with the Dynamo stack. Prefill disag is super interesting, but it's also a little bit more tricky, right? You need a little extra hardware. You need performance to move that KV, so you need to have the network backplane to support that data movement. It's also a little bit more dependent on your model. NIM is going to help you with that. Models that are very helpful or like the different configurations for prefill and decode, that's going to be provided to you by NIM itself. But feel free to play with it. If you're like a DeepSeek, you're definitely going to want to think about that one. All right, now we're going to look at code. And I don't know which button to hit. I think it's the green one. It is the green one. Excellent. We're going to look at code before we get in that. The library is broken up into two parts. We have our core Dynamo runtime and our Dynamo LLM, separated out so that they're logically, all the LLM bits are, guess where? In the LLM. All the runtime bits are in the runtime bits. That's mostly written in Rust, and then our bindings, you can see them there in the lib bindings Python. The mixed wheels, the wheels are built with Maturin, just mixed bindings. We're at 0.1.0. We just released today. It's not mature. We're getting there. We are so excited to build this in the open source with everybody, but we are just at the beginning. This is exploratory, and we're going to have so much fun building this out. So we made everything public, like all the way down. Source code's public, but even the internals, like right now, we're maximizing pub on everything, so like you can touch all the internals of the library. Eventually, we're going to consolidate that API. So over the course of the first few months, we're going to kind of open it up, give everybody access to all the internals, see what you can do about it, and then we're going to start making logical compressions of that API. The 4 things, top-level objects down here, are going to be your distributed runtime object, your namespace component, and endpoint objects. These are the core building blocks that we start at the bottom and you build the whole LLM stack up off of. These are the 3 most important things when addressing. When you want to run something in a distributed environment, so whether you have 2 nodes or you have 10,000 nodes, you need an address for those things. And we address all the components, all the runnables out there with 3 things: a namespace, a component, and an endpoint. Namespace provides a logical grouping, generally like if you have a distributed model like foo, bar, llama 3, you might put it in a namespace. That way your preprocessor is isolated to your namespace, so you can have preprocessor in different model spaces. Your component will be your router, your preprocessor, your backends. Those can either be services. They're also like logical points for emitting events. They're also logical points for configuration on the discovery plane. These are just addresses, and then I'll show you in a second how we actually serve something. Components can serve functionality or handlers on endpoints. So a full function, like a full remote procedure call, requires a namespace, component, and endpoint. And I'm supposed to watch the time real quick so we don't blow over. I've got 7 minutes. I want to serve this function. Super basic function, request handler. This can be stateful or not stateful. If it's stateful, you just plug in your state in the init. And the only thing that you need to do to serve a function in Dynamo is create an async generator in Python. That's it. It's probably one of the easiest onboarding to distributed serving or distributed anything out there. Bring your async generator, and we'll serve it. So in this case, we just take a string in, and we yield each character back. How do we serve it? Well, there's this worker function up here. This is kind of your entry point, and you wrap it with a Dynamo worker decorator. This is what's going to coordinate the Python async runtime with the Rust async runtime. And then you just call into your main application from there. In our main application, you can see right here that we have our runtime. We passed in a namespace called Dynamo. And the first thing we do is generate our address. So our component is our runtime namespace. We give it the namespace name. And then we give it the component in the same place. We're calling it backend. To serve our async generator, we just have to say that the component is going to serve something. So we create a service. That sets up the infrastructure to serve something. Now we need to serve it on something. So we say component.endpoint. We're going to serve it on the name generate. Ultimately, our address is dynamo.backend.generate. And we start the endpoint service by just passing in an instance of the generator. So we create an instance of that class, give it the generator function, and we just await that. Now, if you wanted to serve multiple things, you would want to spawn that off in a task. But at this point, while we await that endpoint, it's being served. How do we call it? Just as easy. We instantiate our distributed runtime. We address it with our namespace, component, endpoint. And then we create a client. Once we get that client object, that await client is kind of magical because that client is getting live updates across the distributed system when new workers come up and new workers go down. So if we hadn't brought up a worker yet and we wanted to await for some to be present, we can just call await for endpoints. So that client is an example of our discovery service at work, live things going up, going down, and reconfiguring the internals of that client on demand. Our clients are essentially routers. You can call generate, you can call random, you can call direct. Direct allows you to actually target direct endpoints specifically. All we have to do is call client.generate. We await the stream, and then we process the stream. And guess what? It says like hello world or something like that. All right. And we can do this in Python, or we can do this in Rust. Just a really quick example of Rust. So maybe the Python people out there in the audience are like, oh, maybe I could do Rust. It's a little more complicated, but got to put a lot of typing and stuff on there, but it's super performant. And guess what? The compiler checks a lot of your errors for you. It's pretty lovely. One of the things I just want to point out at the top, you see that we have single in, many out. The entire Python API is single in, many out. The Rust API can be far more advanced, although we only have implementations for single in, many out. We do have ambitions to do that more in the future, but we want to focus on what we're good at. And again, you can call it in the same way. Rust client looks much the same. That's the request response paradigm. The next thing that's most important, you saw examples in the talks, is the event plane. So we do events via pub/sub mechanism. That's core built, or like our pub/sub broker in the background is Nats.io. It's fantastic for this purpose. And what we do is we apply traits to each of our 4 primary components. This is a hierarchy of addresses. So you can emit events on the distributed runtime, which would be a global event, which everybody in the entire system across all your 10,000 nodes would see. You can emit it on your namespace. All your components within that namespace can see those events. You can emit it on components, and likewise down to functions. And so it's just a convenient way to address them, and so that you don't have to come up with random different names to avoid name collisions in there. And mostly we emit our events in JSON, but if you want to use your own Serde, like if you want to use whatever, bring Captain Proto or something, you can use the bytes variant. This is what it looks like. It's in Rust code. All you do is create a distributed runtime. Here, we're going to do it on the namespace. So our namespace subscribe. We got our subscriber, namespace publish, and then we'll just pull the subscriber, and voila, our test passed. Discoverability. This is kind of the magic in the distributed system. You have 10,000 nodes. You have lots of processes. You really don't want to manually configure all your different things. And you want to actually configure them in the right way. This is a huge, huge challenge, and something that you have to really think about and get right when you scale out. So our discoverability is going to be core based on etcd. Right now, we don't have an API for it. It's just using the raw etcd clients and a second level client that lets you do atomic. So the create is an atomic create and validate, make sure that the thing that you would have put there is actually the thing that is there. If not, otherwise it throws an error. And finally, the last one is the get and watch, which is the magic that makes the client auto update based on a worker availability. Again, this is a work in progress. We'd love for people to kick the tires and give us some good feedback. The LLM components are written in the Dynamo LLM crate. I've listed them out. The HTTP service is our OpenAI HTTP service. It's used Axum for that. Preprocessor does the prompt templating and tokenization. The model card is super important. I'm going to talk about it below. The KV-aware router is where all the magic that Tanmay talked about and Neelay. The disaggregated router is also there. And then we have some convenient wrappers for tokens and tokenizer. Model deployment card is the last thing I want to touch on before I'm done, and I have 1 minute to do that. Let's see if I can get it done. I might go 1 minute over. Sorry, guys. The biggest problem here is that in a distributed system, you want to make sure that your preprocessor, your router, and your backends are all using the same pieces for that given model. You screw up the tokenizer on your preprocessor, your backend is going to output garbage. And what kind of garbage does it output? You don't know. Like maybe it's semi-okay. We want to nip that in the bud, and so we thought about this pretty deeply. Our model deployment card is a set of assets that the model needs, that the distributed components need. So you instantiate your preprocessor with a model deployment card. You instantiate your router with a model deployment card. And one thing publishes your model deployment card to the discovery service so that when you pick it up, they're all happily in sync with each other. I think this is really, really important. I'm hoping that the community gets behind this and we can broadly adopt a model deployment card across different backends. I think this is super, super important. And I think with that, I will, the last thing I'm gonna say about the model deployment card is that you can chain the hash of the deployment card. So you take a hash of that value, the bytes, in your model deployment card, and you propagate that with the request as it goes through the system, so that as a request goes from preprocessor to the router to the backend can look at the request and say, I know the hash of my model deployment card, and I see that the hash of your model deployment card matches, I'm good. I'm gonna take this request. Doesn't match? Well, I'm gonna call panic or something. I'm done. I don't know what to do. Someone done screwed up and we don't know what to do anymore. Okay, with that, I think we've got Harry. I'm gonna get Harry's slide for him.
Thanks, Ryan. That's an awesome design. I only have 2 more slides, and so I wanted to talk about the next steps. The first immediate next steps, we really want to get your feedback, and we also want to collaborate with you. That's the whole reason why. Thank you. Yes. We really want to collaborate with you, so that's the reason why we are doing this out in the open. And so please try our stack, and then we'd love to get your feedback. If you have any issues, please file it on GitHub, and then we'll get to that issue as soon as possible. And also, we have a Discord set up, so you can talk to us directly with our engineers and also solution architects. In terms of the features that are coming soon, there are 2 major features that we're expecting. First one, as we talked about before, we wanted to enable KV cache offloading, so KV manager, that is capable of managing the memory at a different memory hierarchy, so including system memory or GPU memory, system memory, SSD, and then also object storage. We'll take the same approach that we took with Dynamo, and so we want to take best of both worlds of Rust and Python, and so we are going to have it written in Rust for performance, and then also Python for the maximum extensibility. There's a component that we didn't talk about in detail, but we have a component that will be released very soon. It's called Planner. And Planner's job is to do real-time performance tuning at a data center scale. And so we're likely to release something around disaggregated serving, so being able to dynamically allocate prefill and decode. But what we think that this should be is almost like a full-fledged reinforcement learning platform. And so if you think about it in a data center scale, if you can actually have the user or the developer set up an objective, say, for example, throughput constrained on, say, TTFT or ITL, and then you can tune for the policy to find the best ratio of prefill and decode, and then the state would be kind of the system configuration. That's kind of where we want to get to. So being able to have the developers use that framework almost as like a reinforcement learning platform and being able to tune it. Ryan already mentioned this, but we have NVIDIA NIM that is going to support very much accelerated deployment to your data center. And so it's going to be as easy as specifying the number of GPUs, what is your SLA, and then being able to just specify the model, and then you should be able to deploy it right away. If you want to connect with us, we have 2 sessions. So we have 2 Connect with Experts starting today at 4 p.m. And then there's also another one at 9 a.m. And so if you'd like to talk to us directly in person, we'll be there. We'd love to see you. So that concludes our talk. Thank you so much for coming. And we would like to now take questions.
Thank you very much, Harry. Thank you, Neelay. Thank you, Tanmay. And thank you, Ryan. So we have a few more minutes for questions. So if anybody has a question, do we have extra mic in the room? Is there an extra mic for the questions? If not, I'll just walk down through the front here and maybe we'll start with you.
Thanks for great talks. And I'm just wondering whether you guys considering hybrid configuration or like throttling power consumption? Because I think this reminds me of the split-wise paper, and I thought like the best benefit of having this kind of multi-nodal configuration is that of course we can handle different kind of workload characteristics like a prefill and decode, and then some guys have some compute-bound characteristics, and another guy have memory-bound bandwidth, and then the best gain probably coming from hybrid configuration, like H100 versus A100, as written in the split-wise paper, like 2 years back then, or like a power throttling, again suggested by Splitwise. Have you considered that kind of approach?
I think the consideration. Did you consider the splitwise implementation?
Yes, different GPUs.
Yeah, the combining different types of actually, I think this one's on. So the question is around being able to do disaggregation across different types of architectures and GPUs. Yes, that's definitely something that we're looking at. And I think to your point of being able to maximize the efficiency of the different stages, right? Yeah, so we're looking into it for sure, definitely.
Hi, I'm Dennis, machine learning engineer. And how does it support auto scaling? So we have application metrics, you know, that
Oh, that was me. Sorry. Yeah. We're on the same RF.
Oh,
thing,
okay,
so
okay.
You talking all.
yeah, no, that's it. I guess basically you're giving us nice application metrics, and yeah, wondering how auto scaling kind of works in the background for request models.
I mean, I'll go start. I mean, I think we are leaning into Kubernetes as being the first class kind of deployment. We're trying to build things modular enough that you could use other types of orchestration frameworks as well. But our first plan is to support auto scaling through Kubernetes, but to give it, again, LLM-specific metrics to look at and to be faster than like a standard Prometheus loop.
We're also considering supporting Storm. So if you're interested in that, please let us know. And then we talked about Planner, the component that was mentioned in the next step. And so that will also facilitate how to auto-scale depending on your required SLA. So those are kind of the approaches that we are taking.
Really quickly, Harry, one more thing is that we support scaling by discovery. So with previous disaggregated systems, you would have problems with FPI or other distributed communication protocols maxing out on the number of devices that you visualize with Pixel and with Dynamo. Now we have a set of systems that allow you to do discovery of new nodes that can be brought into the system and completely integrated into the communication topologies that are used.
So if I brought up a new node,
yeah, so if you bring up the new node and you register the discovery, you'll be able to use that node. It'll be instantly routable once it basically registers itself with the system.
Do you guys, sorry, you guys had talked about the different types of memory that you guys are going to be supporting. Are Grace Hoppers and Grace Blackwell is going to be like a first-class citizen on the ARM front to be able to offload to the unified memory to take advantage of all this?
Absolutely.
Yeah, definitely.
Yes, absolutely. Like Grace opens up so many doors with the speed at which we have it. It becomes a new level of hierarchy in the system, right? So on Grace, you just have bigger and more, right? And so more is better. Like literally with this, like it goes to Jensen's thing. The more you have, the more you can cache, and the more you cache, the more you save.
We have time for one last question.
Hi, I'm Junda Chen. I'm actually one of the authors in this serve, which is one of the first batch of work in PD disaggregation. And my question is along the planner. And I guess when we're doing the work, one of the biggest challenge was to kind of handle this workload shift. If you have a workload shift, that means you need to reconfigure the configuration of the whole cluster. So I wanted to know how far you guys have been in this space, and essentially how quickly can you actually change this configuration on this model serving. Thank you.
Great things about I'm going to back up here so I can get it. One of the great things about the discovery service is it allows us to do live configs, so it's easy for us to push it out. How we would automatically reconfigure those things live, we'd have to do some sort, and we don't have this yet, but like how we would think about doing that is if we needed to say change, like we had 50 or 70 decode workers and we decided that we needed to make a change, we would basically do just a rollout. And the router, if we had router limitations, I think that would be challenging as well, but we could just choose to route new requests to the new specific requests, maybe to the new workers. It would be a challenge, but I think probably a pretty interesting one. You guys probably have some really good ideas on that too. So.
Well, definitely thank you for your work. I mean, I think the DistServe paper, as you can imagine, was one of the really guiding lights for us. So we really enjoyed reading that, read it many times. And Kyle in the back is actually one of our tech leads, and he's working on the planner, so he probably has a lot more details about what it's going to do.
We actually credited your paper on our GitHub. So.
I got confused. I think we have a little bit more time for additional questions. So if anybody wants, yep.
Hello, I'm Arthur Rasmussen from Weka. I helped with some of the GDS stuff. I have a question regarding NIM. When we deploy this Dynamo distributed inferencing architecture, are there additional servers or NIM services that we'll need to deploy for the customer in order to support this, or is it still just like plain TRT?
NIM is I'm going to use this one. NIM is NVIDIA Inference Microservice, where you're going to have NIMs, right? Plural. The great thing is the NIM backend piece will likely be exactly the same. You'll just flip a flag and it will become a backend worker. I think we have to strategize on what the other NIMs look like, but they'll probably be their own standalone containers. I think we have to work with customers to see if that's going to be like an issue or if they want the same container with all the bits built in. Some people are going to want one, some are going to want the other. We're going to have to define what that looks like, but yeah. NIMs.
Sorry, one quick follow-up to that. So there's, it's all just plain TRT. There's no like orchestration microservice that needs to be run separately?
I think it's unclear yet for NIMs, like for an orchestration service. I think we will probably have an planner will be running like outside of like individual models.
Yeah.
And so I imagine that there will be a hierarchy of services that are going on the platform when NIM is running. I think it's less clear what exactly that is yet. So.
Okay, thanks very much.
Hi, this is Pankaj from Base 10. My question is around the SSD offloading component of the KV cache manager. How does it compare to Firefly file system? Because by using multiple disks in parallel over a high bandwidth network, you can almost go up to the CPU, GPU, RAM bandwidth. Is that the goal, or is it very basic, like just to utilize SSDs, where you can, but not in a very optimized parallel fashion?
We want to support every level, all the possible places that you want to put KV, we want to support that. So if you have a local SSD and that's cool, we're going to help you there. But distributed SSD across all of our storage partners, everybody wants that too. So yeah, we're going to, KV everywhere, right?
Great. So is it in terms of storage or also parallelism across all of those?
Well, yeah, I mean, I think to have a disaggregated storage system, you by default have parallelism. Like I don't think anyone just maybe they do a JBob, I don't know, but it's probably some sort of large striped thing with some metadata servers and whatnot. So
Okay, maybe this is getting in the weeds, but Firefly file system uses CRAC to have large amount of replication so that you can hit a lot of replicas together. Is that the idea, or the storage unique and a little bit replicated, like 3x, not 100x?
Well, that's kind of the thing with KV, right? It's like if it's not there, you can just recompute it. So it's not like we have to have it there. So we don't need like a fully consistent. If we have misses, we're just going to recompute. So it just means it costs us a little bit more. So yeah.
Thank you.
Yeah.
Hi. I think this is the first time that I've seen that NVIDIA is like, oh, to run something like this, you need an etcd cluster and an NAS cluster, but it is like data center level. I'm curious how you see that kind of evolving, and if you see like this approach, sort of the hierarchical approach, expanding beyond one data center in the future.
Oh yeah, absolutely. Like we love that. Like the more data centers, the better, right? And I mean, if you think about it, bouncing from one data center to another, like it's not that much time to move a string across the world and execute it someplace else and stream that response back. You pay a constant cost to get it there, and your first token is delayed, but everything else is going to come in at the rate at which it was emitted on the other side of the world with just that little bit of delay. So taking advantage of the world and the data centers across the world and the time of day usage is absolutely part of the large scale, like, what is it no, I was thinking about Hitchhiker's Guide to the Galaxy, like the whole world computes for years and years and years, and the answer is?
42.
That's it.
Yeah.
Cool. But what is the question?
Hi, my name is Karthik from Escape Photonics. You said the prefill is compute bound and the decode is memory bound. Can you describe how your resources will look like between the prefill and the decode? Like, it's just the number of resources, or the type of resources is different? I mean the hardware resource.
Certainly the number. So your metrics, like your distribution of requests, you're going to have some amount of prefill coming in. That is like the ISL load that's coming into your system at a given rate. And the number of prefill workers will obviously be directly correlated with that. So if you were summarization heavy, say, you would have large ISL coming in all the time, you would have more prefill workers. If you are multi-turn heavy, that's actually the other end of the spectrum. Multi-turn is going to have a lot of cache reuse because you're going to see a lot of the same stuff. That's actually going to push your prefill number of workers down smaller and take advantage of the cache. So you have more decode workers and you'll have more cache. And there you fall into a pattern of you want to have some sort of cacheable load. So if you are above your cacheable load, or there's like a cache limit or cache load limit, if you're above that, you're going to be in a really sweet spot because you're going to be caching more. If you are below that limit, that is a metric that we want to expose. And then essentially that metric is cache evictions, and cache evictions are going to then cost you prefill time. So it kind of then spirals back down. So there is kind of this level. Like if you have enough, you will cache enough. And if you don't, then you will spiral back down into requiring more and more prefill.
So if the requests are coming in more or less like homogeneous way, let's say I have a very large context, 128K, right? I get like hundreds of requests of same context length. Do you see a benefit out of this? Or because everything is now going to be back-end, after the prefill is done, it's all going to be decode limited, and decode is memory limited, so you don't have enough memory bandwidth. That's all given, right? A GPU has a specific amount of HBM bandwidth.
One of the things you can also do with disaggregation is you can change your parallelism strategy as well. So your decode worker can be like TP8, and you can have your prefill workers just like TP2 or TP1, and so you can get back some of that as well. All right, so you can trade. It's not just about the number, but also the way the model's built can be changed, and the parallelism that's one of the big things that we've been looking at, right? Is so when we get the most optimal numbers, that's not with a uniform parallelism. That's with a mixed parallelism.
Right. But the numbers you showed is all for a context length, like you were saying, like 1K, 2K context length. Like have you tried for a larger context?
Yeah, when you look at like the proto curves and all the different dots, we scan a large number of different, so our data sets, a lot of times we show like fixed size synthetic data sets just to give like a snapshot, but like we test it all, and we have real world data sets that have a variety of stuff in it. So like, and every one of these problems is generally specific to the customer, right? The customer has certain data patterns that they see in their workloads. Sometimes they're completely new to us. And so you can, the more fixed and more predictable your distribution is that you see, the more optimizations you can make. If you have a very predictable workload, you can start thinking about even specializing hardware between these. But I mean, when you specialize, and then you are less general. And I mean, that's, you have to make those risk-reward trade-offs for yourself. Yep.
Got it, thanks.
To answer your question a little bit more directly, so the test results that we displayed here, it takes cost to actually produce them. So we've done some simulations and tried to see if it matches. So the result that you saw actually matches with the simulation, but also we simulated all the super long length context and all these things. And so we kind of have a good idea as to what behavior we should expect. And so it confirms with the pattern that we expect.
Hello, my name is Jessup from Avian. Good to see you, Harry and Neelay. Good to see you. I was just wondering how Dynamo works with like one GPU nodes. Like, does the worker routing still work? And have you been able to see maybe benchmark improvements? Even for those nodes, does it mostly come from the KV cache related improvements or things like that?
Yes. Yes. No, yeah, we do a lot of, so we kind of built each of the pieces independently. So we've got a lot of experiments to show, even with single node, 8 GPUs, even with a small model, even with an 8B, we get benefits from the KV-aware routing.
Thank you.
I think we're done.
Any further questions? We've got 3 minutes left. Okay. Yeah. Well.
So you were showing like one large, I'm sorry, I'm Riela Desus, I work for AWS. And my question was like, what's the dynamic for multiple models? Because you talked about like one large model. Like if I had, multiple large models or a mix of small and large models, like what do you need to consider to make it work with this architecture?
Sure, that's what we call Planner. So Planner is going to be this data center, this watcher that watches over not just one deployment, but all your deployments. So if you have a fixed size capacity, but lots of different models, Planner is going to make the choice of how to dynamically partition the resources, given the loads of each of those models in an optimal way. That's the dream anyway. We're going to get there.
One quick question on that. When you reallocate between the decoding and the prefill workers, are you typically doing that with a particular API? Like, are you loading it with weight streaming? Are you loading it with GDS, using a normal POSIX interface for loading?
The models itself, hopefully we can just flip the switch and they change behaviors. Not
you mean like, you don't need to reload the memory?
No.
Okay.
Ideally, no. Some backends that don't support that, we do have to reload, but many backends are flexible enough that we can just flip a switch and they just change behavior.
Okay, fair enough. I think she had asked a moment ago about multiple different models. Is there any conception of swapping dynamically between prefill and decoding with a multi-model environment? Like, as in, if you're running a managed inferencing service and you serve, like with Cohere, they do Command R plus, Command A, and maybe it's in one large single inferencing pool, and maybe they need to swap between decoding and prefill with multiple different models.
Yeah.
Okay.
I don't know quite how to answer that.
All good.
We want to be super flexible about bringing up and tearing down workers and like actually making that policy very configurable and letting the users and developers be able to define the policies. So I think if you can dream it, we'd like you to be able to do it. That's the goal.
Okay, with that, thank you everybody for your time.